All right. So basically, if we're doing this problem, here, I'm gonna see if that gets the echo chamber going. All right. If we're solving this problem, my thought process to do this is always the same thing. And what I mean by always the same thing, I mean if I'm going to solve this problem, I want to consider what's actually happening as a mechanical energy initial equals a mechanical energy final. Okay? If I'm thinking about it in terms of energy bar graphs, I'm thinking that I already know that the car is somebody's going to put some gravitational potential energy into it, and then I'm going to get some kinetic energy out of it. So in terms of a bar graph, I know that I'm looking at all of the energy initial is in kinetic because it's not moving, because it starts up here. It doesn't say it's at rest. I'm going to assume it's at rest. And then I know down here, I will get a maximum of UK. Really, that's all the help I need to start to solve this. And so Calvin's absolutely right. The mg height initial is going to have all of its energy to begin with, and then we would like to convert all of that into 1/2 mv squared. Now, there are people out there that like to solve the problem like this, and this is not wrong. Some teachers like you to keep track of both types of energies on both sides of the equation and solve it this way. We know that it's not moving to begin with, and we know that down here, this is our reference line, so we set it equal to 0. Either way, you've got the equation set up the way Calvin said to set it up. So let's take 50 right here. You know what? I'm going to use 10 for gravity, just because it'll be easier, my calculations. It is A-okay to do this anytime you solve a problem on the AP exam, provided you set out your answer to begin with. They tell you to use 9.8, and then you have to use 9.8. If they don't tell you, then you're welcome to do whatever you want to do with that. Oh, and look at this. Some of you out there probably looked at the M and said, man, I could go ahead and take that out both sides too if I really wanted to. No harm in that. So our answer for A is to take 100 and double it. So the algebra actually becomes radical 200 equals VF. And I'm just doing some algebra down here. I'm adding 2 to both sides to get rid of that quantity. And then that gives me radical 200 for my final velocity. Does anybody have that number? Oh. Got my calculator here, so I can do it. 14.1.
Yeah, that's what I got. Well, I got 14 exactly, but I did 9.8 meters a second.
Let's do 2 sig figs. There. We've got our answer for A. B presents for us the same challenge. All right? B presents for us the same challenge, but let's take a look at what that challenge really is. At this location, sorry, I'm skipping ahead. No, I'm not skipping ahead. It's funny. Question B refers to point C. So that's kind of funny, right? At point C, it's still my car. And at point C, initially I put in all this potential energy. And at point C, now I've got to acknowledge that there is some potential energy contained within it, and it has kinetic energy. So originally I had all this gravitational potential energy initial. And now I've got this energy final, which is kind of going to be a combination of gravity and a combination of kinetic energy. And we don't know which one's bigger, really, although I can tell you right now, it looks like it's going to have a little more gravity than kinetic energy. That's why I went. So I suppose I should have done it this way. A little more gravity final than it had kinetic energy. And our problem should solve that out. Right? So, we know that meow equals meow. And we have this mg initial equals mg final now. Look, if you don't keep track of the height, then you are going, oh, that's 7 meters below that. Sorry. It didn't make anything I said wrong other than the fact that gravity is now going to be smaller than kinetic energy. I saw that -7 and that threw me off. The reference of the problem threw me off, but I'm back. I'm back after it. Now, truth be known, we don't need any of the m's. They can all come out to help us solve this faster. 10 times 10 equals 10 times, if I'm 3 below my reference line out of 10, I've got my height of 3 plus 1/2 of my v squared. So I'm actually looking at 100 minus 30, 70. I'm just doing like some shortcut algebra, if you will. Shortcut algebra. 100 minus 30 equals 70 times 2. I think screw that. Yeah, I like what I've done here. That sounds good to me. Clear. So that's the square root of 140. My new number, people, is 11.8 meters per second. What do you think? Do you all agree with me? Have I done my math right? And do you like my line of reasoning?
I agree with that.
Okay, awesome. So as long as everybody's cool with that, I'm going to erase A. I'm going to solve C in its spot. Ran out of room, people. That's all. So let's take a look at C. Question C. What is the force of friction applied to the cart if the cart travels 35 meters in total and stops at point C? Okay. There. Point C is now saying that all of the energy we used went into work done stopping the car. So we would just change this up. Work done by a non-conservative force? Well, gee whiz, Matthew, that's pretty easy. That is mass times gravity times height equals force times distance. That problem is a lot easier to solve than you would think, in my opinion. So there we go. So we're going to say this non-conservative force. I've got 143 newtons. That's the average force. It's an average force, people. Obviously, it's going to go up and down depending on where you are in this scenario. But they were very, very vague with what 35 meters entails. So, with that in mind, are there any questions? That's our journey. If there aren't any questions, go ahead and open up